Thank you, and I am going to turn it over to Eddie Santosa.
Thank you very much, Jill. After Jill make a good presentation about the daylight at LMN, I would like to share what we do at Callison. We are a 1,000-person architecture firm, and we do different type of building, from specialty retail to workplace environment. We have 10 different offices around the world, from Seattle to Shanghai in China. In our performance simulation team, we have people in Seattle, Mexico City, and Shanghai. We consist of 14 people with one specialist, which is me, and we train people from architecture studio to do energy simulation and daylight simulation. This is one of the session training that we have. In terms of daylight simulation, we put it in a bigger context of performance modeling. This is our typical approach that we want to implement ideally in all the projects. As you can see, it started with establishing energy target to delivering energy modeling for the lead compliance. If you see the fifth row, it's actually a daylight analysis. Ideally, we would like to do it in early design, at least until the SD stage. So you have opportunity to play with your meshing and the shape of your building. In our daylight simulation, this is our typical process. There is two major software that we typically use, a DView for our climate analysis, and a DIFA for Rhino for our daylight analysis. For architecture firm, I think for the people to learn daylight simulation, I think the most important one is to understanding daylight metrics and the sky model. This is the key to do a daylight simulation. After we talk about the background in our company and how we set up the group, I would like to share two interesting case studies. Both are interesting because we couple between energy performance and daylight performance in the space. The first case study is a retail project in Dubai. This is our initial design sketch from our design team. As you can see, our goal is to focus to provide the daylight in the corridor space and the food court area. As you can see, it's actually we provide a good daylight or design scheme by putting the skylight on the east side and the north side of the corridor. If you follow the rule of thumb, it's the best design. However, we test with our energy simulation. Our current design actually performs above 200 kilowatt hour per square meters. We're also experimenting with a different type of scheme by eliminating all the skylight, putting only the 15% of area of the skylight and 30%. And we can see our initial design actually not perform really good. Other scheme perform below 190 kilowatt hour per square feet. After we assess the daylight energy, we want to see how's the daylight in the space, especially in the corridor. We play with 4 different options in the beginning. If you see, the option 1 is actually our initial design sketch. In option 2, 3, and 4, we introducing different type of shading device and light monitors. For example, for the option 3, we have a 15-degree shading device and continuous light monitors. We test our daylight simulation at June 21st, 1 o'clock, because it's one of the peak load in the building. We use a standard of 200 lux to 500 lux. 200 lux is the minimum IS luminance recommendation for the corridor space for the retail building. So this is a result of our simulation. The first image actually showing the rendering or the luminance level. The second one, the second column showing the illuminance level. Our target is showing around the blue color, which around 200 to 500 lux. You can see our initial design is showing a problem also in a daylight. We achieved more than 30,000 lux on the space. So you can see the correlation between bad building in the energy performance and the daylight. In our option 2, it's getting closer with our target. It's 750 and 300 lux. And this is our option 3 and 4. It's getting better and better in terms of like illuminance level that we want to achieve. After several iterations, actually we choose this option with a clerestory window and a skylight with a diffuse type of glass. You can see the illuminance level, we can achieve the target around 300 and 400 lux. After you see the evolution of illuminance, you can see when starting we have really high illuminance level, but in the end we can achieve the targeted illuminance target, which is around 200 to 500 lux. We also use this approach in another space, in the food court area. I will just go briefly in the food court area. This is our initial design and comparison with our improved design. As you can see, in our initial design, we have 2,000 lux. And in our improved design, we have 500 lux. What we do to make it better? There is a 3 strategy that we change in the building. The glass that facing south part, we change it with make additional perforated metal in the outside and a fritted glass in the inside. We also introduce a diffuse glass in the small skylight in the ceiling. After we talk about the retail space in Dubai, I would like to share a project in Abu Dhabi. It's a triangle-shaped office tower. In here, our goal is to optimize the facade and using the energy and the daylight simulation to make sure that we have low energy building and a good performance in terms of daylight. In here, we use energy simulation as our assessment tool. Probably most of you familiar with EQuest. EQuest is mostly people use for LEED compliance or code compliance purposes. In this case, we're comparing 4 different schemes. Our initial design is a sleek tower building without any shading device. You can see the performance of EUI that's showing 100.3, and also we can also see the performance of daylight from how many percentage of electrical lighting that we save. In this scheme, we have saving of 48%. We introduce a shading B and D in the option 1, which is a vertical shading and accurate shading device. This is each shading that we apply in the facade. And you can see the energy performance is dropping, which is getting better. But we compromise a little bit in daylight performance. The more energy saving from a daylight, from the electrical lighting, it means that the more daylight that we introduce to the space. We also test the perforated metal by adding a shell in the building. And you can see we compromise a lot in the performance of daylight, although in the energy performance we're getting better. We only introduce a daylight and saving the energy around 35%. Our preferred option is actually the last one, which is we balance both. In terms of like energy, we're not the best one, but we also still get a lot of daylight and view for the building. In the EQuest, our typical result is from LS-I. So if you don't have a daylight simulation and you have a LEED project, definitely you have an energy modeler. So you can ask your energy model to test the daylight also, the performance in the building in each zone area. In here, it's showing the electrical lighting usage saving in a year. It's showing a month and also showing the every hour saving. You can also learn about the illuminance level in space. Every zoning, they will have a report that you can pull out and see the illuminance level in the building. So it's very handy if you don't have a daylight consultant in your building. This is not probably the most accurate compare the radiosity or ray trace simulation, but it's good enough to drive your design, to make a decision what type of design that's better for your building. In conclusion, we can see the daylight simulation is no longer only for LEED compliance, but it's also for making a better design, high-performance building, and comfortable space. We also see the rule of thumb is no longer valid. It's no longer sufficient to address the needs of sustainable design. Thank you. And I will hand out to Joe.